Okay, let's do one more problem. We'll consider this one, right? First, we need to find the complementary function. Then we need to find the particular integral. Then sum them up to find the complete primitive. Now, when you find the complementary function, you need to consider homogeneous equation, where the right hand side is in which the right hand side is equal to 0. So this is what you have. Now you try this one. This is this usual trial, but there's a reason for this, reason behind this. But I'll explain this later. This one. Now you go for the first derivative and the second derivative. Here note that we force k to be non-zero to avoid getting the trivial solution. Okay. Now you plug in those results here and pull out the common terms, and you will end up with this in the parentheses. Look, it is very similar to this one. Second derivative should be replaced by the second power of lambda. Zeroth derivative by itself can be considered as the zeroth derivative. So zeroth derivative is replaced by zeroth power. So 4 times lambda to the power 0. That's why you get 4. This is forced to be non-zero. This is always non-zero, leaving this one to be 0. So you will get these two values for lambda. If you compare it with alpha plus or minus I beta form, alpha is the real part, it is 0, beta is 2. Thus you can write the complementary function in this form, e to the power alpha x, k1 cos beta x plus k2 sin beta x. However, alpha is 0, beta is 2. E to the power 0 is 1. Therefore, this will be your complementary function. Now go for the particular integral. In the case of particular integral, you consider the full equation, the given equation, because the particular integral is the solution to this differential equation. Now, what would you try? When you have sine 2x, you try this one. You try try a linear combination of sine and cosine with angle 2x. At the same time, this is fine as far as these functions are not in the complementary function. But unfortunately, look, these functions are here. Therefore, what should you do? When you have the same function, so at least one function in the complementary function, this is your regular trial. You multiply this by x. So this is what you would try. Then you can get the first derivative. It's a piece of cake to you. Then get the second derivative. This is second derivative. Now substitute these results here in equation 2. However, you don't need the first derivative here. So this is y. This is the second derivative. So you plug in those results, which is equal to sine 2x. Here there's something that you need to note. Now, you need pure sine 2x, right, in the right hand side. But you try this one. These terms carry x. X cos x or x cos 2x as well as x sine 2x. But look what happens here. You have 4ax cos 2x. What do you have here? Minus 4ax cos 2x. So this term will go away with this one. And at the same time, this is bx sine 2x. This is minus 4bx sine 2x. Of course, here I have missed the bracket. Here it is, of course, 4bx sine 2x. Here minus 4bx sine 2x. So even though you try, you multiply the regular trial solution by x, those terms will go away once you substitute those results. That's a must. Right? If those terms are left, that means you have made some mistake, algebraic mistake. Now what about this one? This one will go away with this, leaving only 4 terms in the left hand side. Of course, you could have omitted this step, but since this is our first problem, I inserted that one. 2b cos 2x, here you have another 2b cos 2x. So you have 4b, these two will, you will get 4b cos 2x. And there are two terms carrying sine 2x. Minus 2a sine 2x, here again you have minus 2a sine 2x. So those two combined will give you this one. So this is what you have. Comparing the coefficients of cos 2x, 4b is equal to 0. Again here, there's a little mistake. It should be sine 2x. If you compare the coefficients of sine 2x, minus 4a is 1. So you will get a is equal to minus 1/4. So this is your trial solution. A is minus 1/4, but b is 0. So this is what you get, minus 1/4 x cos 2x. So this is the particular integral. Now the complete primitive is the sum of these two. So plug in these guys here, where k1 and k2 are arbitrary constants. Now, let's see what kind of a graph you get. Here there's something that I want to explain you. Suppose that you want to graph something like this. Or, for example, I would say I take something else. Now, this part is completely oscillatory, whether you have sin x or cos x, between minus 1 and plus 1. So its magnitude is 1. However, therefore, the magnitude is decided by this part. That part decides the envelope. It is bounded, it has two bounds. Like, take sin x, for example. The graph of sin x goes like this. It has two bounds. It oscillates between these two lines. This is minus 1, this is plus 1. Because here the number you have is 1. Similarly, if you have x, this is how you graph it. You sketch y is equal to x. Also you sketch minus x. Now in between you show the oscillation here. Sin x is 0 here, like this. That's how you graph it. Even to this side you can graph it in the same fashion. Here, this way. Because when you have small positive values, both are positive. When you have small negative values, both are negative. So here the sin x is positive. Here you have a shape like this. Elsewhere you see the oscillation. So that's how you graph it. So let's see what kind of a graph you get when k1 is 1, k2 is 0. Here. When this is 1, this is 0, you get cos 2x minus this. So you will end up with this one. So this part decides the envelope. It's enveloped by, the graph is, the oscillation is enveloped by two functions, two lines or two curves. So this gives you the envelope, this decides the oscillation. So you draw this one, 1 minus 1/4 x. Here it's a straight line, intercept is 1, gradient is minus 1/4. So it meets x-axis at 4. Right, look, 1 minus 1/4 times 4 is 0. Similarly, you draw this one, negative of that. That is minus 1 plus 1/4 x. Now show the oscillation in between. Here, the precise nature of oscillation shouldn't be indicated. It's not necessary. You just draw something like this. To this side also you have something. But here it should be 1. Why? When cos x is 0, this is 1. When x is 0, this is also 1. So 1 times 1 is this. So this is what you get. Look what happens. The amplitude of oscillation grows when x goes up. It becomes larger and larger. Okay. Now, we'll do one more problem, which has a more general setting. Okay, thank you.